Okay, so welcome to one of the classes of condensed matter physics course. And as you know that so far we have discussed about the different properties of metals, and we have discussed in the previous classes about the heat capacity of solids, and we discussed three models that describe the heat capacity of solids. One was the Dulong-Petit's law. That was a classical law to describe the heat capacity of solids. Then it was remodified by Einstein based on the quantum theory. However, Einstein model also could not explain the fall of heat capacity of solids at low temperature. Einstein model predicted that heat capacity of solids should decrease exponentially. However, experimentally it was observed that heat capacity decreases proportional to T cube, and this T cube behavior was very well explained by Debye model, and so we have Debye theory of specific heat, and we also explained the phonon density of states. So we saw that Debye model was the most successful model, and it is till date so most successful model to explain the heat capacity of solids, but at the same time it is having some limitations which are as follows. As we know that Debye model is a continuum model and is valid for long wavelengths only, and when we are saying long wavelength, it means low frequencies are active in the solid. Only low frequencies are active in the solid. And the total number of vibrational modes are assumed to be equal to 3n, where n is the total number of atoms. This is difficult to justify as the solid is considered to be an elastic continuum which should possess infinite frequencies. In Debye model, there was a maximum frequency that any oscillator can possess, and this maximum frequency was defined as cutoff frequency. This cutoff frequency is assumed to be the same for both longitudinal and transverse waves. If we recall that in Debye model, the solid was considered to behave like sound waves. By this, I mean that each atom is considered as an oscillator, and since it is vibrating, so it will generate waves, and it is considered that solids are generating sound waves, and sound waves, as we know that it has three polarizations, one longitudinal and two transverse polarizations. So it was assumed in Debye model that the cutoff frequency is same for longitudinal as well as for transverse waves. However, it is practically difficult to justify because different velocities of transverse and longitudinal waves should imply different values of cutoff frequency for these waves. And according to this Debye theory, this cutoff frequency represented by omega d is independent of temperature, whereas experimentally it is found to vary plus minus 10% of its original value as we change the temperature. This theory does not take into account the actual crystalline nature of the solid that we are going to discuss, that actually solids are crystalline in nature. We will try to understand what do we mean when we say the solid possesses crystalline nature. So this theory means the Debye theory does not take into account the crystalline nature of the solid. The theory cannot be applied to crystals comprising of more than one type of atoms. And this theory completely ignores the interaction among the atoms and the contribution of electrons to the specific heat, as we have previously seen. So these are the some limitations of the Debye model that we discussed in the previous class. And today we are going to start a new topic, that is Bravais lattice. You see the spelling, it is Bravais. It is not spelled as Bravais, it is Bravais or Bravais. Bravais is correct pronunciation. So Bravais Lattice, it is not spelled as Bravais. So it should be spelled as Bravais. So today our point of discussion is on Bravais Lattice. So as we know that matter exists in three forms, primarily solids, then we have liquids or gases. And when we see any solid material, to our naked eye, a solid appears as a continuous rigid body. We can think of any solid. You can think of your mobile phone, laptop, table, chair, anything that comes into the category of a solid. It looks like as if it is a continuous rigid body. But experiments have proved that, however, all solids are composed of discrete basic units which are called as atoms. And these atoms are not distributed randomly. When the solid is viewed at the microscopic level or at the nano level, these atoms are not distributed randomly, but these atoms are arranged in a highly ordered manner with respect to each other. Such a group of ordered atoms is referred to as a crystal. And there are several types of crystalline structure depending on the geometry of the atomic arrangement. So what do we mean by a crystal? A crystal is a solid which has regular arrangement of atoms, or atoms are arranged inside that solid which we are calling as crystal. Atoms are arranged in a particular fashion, and depending upon their arrangement, we can have different type of crystals. So one type of crystal is known as the single crystal, or this arrangement of atoms, it generates the crystalline structure. So we can have a single crystal, and what structure single crystal possesses, that is known as the single crystalline structure. What is there in the single crystalline structure? There is periodic arrangement of atoms, and this periodic arrangement of atoms extends up to macroscopic level. By macroscopic level, we mean that we can have a single crystal of the length of centimeter or even inches also. That is the meaning of macroscopic level. There are other materials also known as the polycrystalline materials, and most of the materials are polycrystalline in nature. They are micron-sized crystallites. Meaning is that single crystals in polycrystalline materials exist up to micron-sized length, and these regions where you have the periodic arrangement up to micrometer length, these are known as crystallites. And each crystallite is separated from other crystallites by a region that is known as grain boundary. Third type of solids are amorphous or non-crystalline solids, in which this periodic arrangement exist only up to a very small distance, on the order of nanoscale, 10 to the power minus nanometer. We do not observe any periodic arrangement up to very long distances. That's why they are known as the amorphous or non-crystalline solids. So as I told you, most real solids are polycrystalline in nature, and this is one particular example of a polycrystalline materials in which the red dots represent the atoms or group of atoms, and you see they are arranged in a particular fashion. They have very well defined separation between each atom, and this arrangement, this periodic arrangement extends from, for example, in this region, this arrangement extends from this line to this line in this direction, and from this line to this line in this direction. And as we cross the line, we see a different orientation of these atoms. Though periodic arrangement is still there, but the orientation of these atoms is different. Therefore, these regions in which the periodic arrangement is there, these are known as the crystallites. And there are several crystallites in a polycrystalline materials. Lakhs of crystallites are there. Here, just to show, it is just a picture, not a real picture. It is just to make you understand how what are there in a polycrystalline material. There are crystallites, only 4 crystallites are there, and each crystallite has periodic arrangement but different orientation of atoms, and each crystallite is separated from other crystallite by a region that is known as grain boundary. So this region, this line between two crystallite, it represents a grain boundary. We can define grain boundary in another way. A grain boundary is a region where we don't have the periodic arrangement of atoms, or where the periodicity of crystallites breaks. That region is known as the grain boundary region. So a grain boundary region is a region of high disorderness. So even if the sometimes these are known as crystallites, and some people call them as grains. So you can call them crystallite or grains. Different people call them crystallite or grains. So here in a polycrystalline material, the grain size is small. Only a small fraction of the atom is close to the grain boundary. As I told you, the third type of solids are amorphous in nature, in which this periodic arrangement breaks up to only in a very short distance. This periodic arrangement breaks. So amorphous solids do not possess crystalline order up to large distances. So now we are going to see different type of crystals. So how we define a crystal? A crystal is a solid in which the constituent atoms, or the atoms that make the crystal, the constituent atoms or molecules or ions are packed in a regularly ordered repeating pattern, and this extends in all 3 spatial dimensions. It extends along x direction, it extends along y direction, it extends along z direction. For example, this is in this picture, this is a single crystal of gallium. So this is a single crystal of gallium. So through naked eye, it looks as if it were a continuous solid. But when we view this single crystal through some experimental technique like transmission electron microscope, then we see that in this single crystal, gallium atoms are arranged in a periodic fashion. So periodic fashion you can understand in a way like you consider the construction of a wall, and you take one brick, then you join another brick. So in a wall, you can imagine that there is a periodic arrangement of bricks. These are other pictures of crystals. For example, this is a single crystal of bismuth. This is the picture of a single crystal of sodium chloride. That is the salt we use in our kitchen, sodium chloride, you know. And this is the crystal structure of sodium chloride. It possesses FCC crystal structure in which we have 2 interpenetrating abscissa lattices. So one is from sodium ion and the other one is from chloride ion. And you can see the sodium ion and the chloride ion, they are arranged one after the other in the sodium chloride structure. We will discuss it in more detail later. So when we say crystal, and we are saying that crystals possess periodic arrangement of atoms or molecules or ions, but if we see the crystal as a whole, despite an underlying crystalline structure, the crystal itself may not appear regular in shape. So this is also, we are calling it as a single crystal, and when we see through the naked eye, it looks having any arbitrary shape. But when we view this single crystal, there is periodic arrangement of atom and it extends up to very large distances. So other examples of crystal, one is famous example is silicon, that is a very famous element that is used to make the semiconductor devices. This is the single crystal of silicon, and you can see it has some definite arrangement of silicon atoms. Each silicon atom is surrounded by 4 silicon atoms. So each silicon atom is tetrahedrally coordinated with 4 neighboring silicon atoms, and this arrangement of tetrahedrally coordinated silicon atoms, it extends in this crystal throughout. Other example of a single crystal is crystalline silicon or silicon dioxide. This is also known as silica. It also has a definite crystalline structure. And what is definite in this crystalline structure? Each silicon atom is surrounded by 4 oxygen atoms. So you can see here, this is the enlarged view. This blue circle represents the silicon atom, and the red spheres represent the oxygen atom. So each silicon atom is surrounded by 4 oxygen atoms. So we say silicon dioxide is an example of tetrahedral oxygen termination. And this periodic arrangement extends up to very large distance in case of crystalline silicon dioxide. Then we have amorphous silicon dioxide also, that is known as silica gel. I believe that you might have seen silica gel. That is a very common material that is used in desiccator to keeps the moisture away from our materials which we keep in desiccator. So silica gel possesses amorphous structure, though its chemical formula is SiO2. It is also silicon dioxide, but it is having amorphous structure. And as I told you, in an amorphous solid, the periodic arrangement is only up to very short distance. It does not extend far. Therefore, in this silicon dioxide also, this type of arrangement does not extend up to very large distance. And you can see here, the local symmetry is the same as that of the crystalline SiO2. However, translation symmetry is missing in amorphous silicon dioxide. Translation symmetry, we are going to discuss it in a short while, but for the time being, I can explain you. By translational symmetry, I mean that whatever arrangement and orientation I see at this point, if the same type of arrangement I see here, that is the meaning of translational symmetry. That if I go from one place to the other place inside the atom, then I must see the same type of arrangement and orientation of atoms. But in case of amorphous structure or amorphous solids, there is the lacking of translational symmetry, or translational symmetry misses in case of amorphous structure.
Sir,
Yes.
sir, in the previous slide, it's written that the locals, no, after this. So
Which slide?
after this slide, sir, the amorphous one, sir. Yeah, the local symmetry is the same as the crystalline SiO2.
Yes.
So what is the local symmetry?
By local symmetry, we mean if we look at a nanoscale, at a very small distance of the order of angstroms. So if we compare a single crystal of SiO2, and if we compare the amorphous amorphous structure of SiO2, then and we are looking at the nanoscale or the angstrom scale, then we have some periodic arrangement. But if we look at a large scale, at the macroscopic level, this periodic arrangement is missing in case of amorphous SiO2, but it is there in case of crystalline SiO2.
Okay, sir.
So in some of the solids, for example, we have seen SiO2 is having the tetrahedral coordination of oxygen and silicon atoms. In some of the solids, we can have what we call as octahedral oxygen termination or octahedral arrangement of oxygen atoms. You can see this is the octahedral. It is having 8 faces, and you have one atom sitting at the center of this octahedral, and there are 8. It is surrounded by 8 oxygen atoms. This is many crystals possess this structure. For example, one type of structure is perovskite structure. Its general formula is AbO3. In this type of structure, we see this type of arrangement in which one atom is surrounded by 8 oxygen atoms. Or for example, if you have heard barium titanate, BaTiO3, it is a very common ferroelectric or piezoelectric material, and it possesses that perovskite structure in which titanium atom is surrounded by 8 oxygen atoms. This is another type of example of single crystal of aluminum oxide, in which each aluminum atom is surrounded by 6 oxygen atoms. And aluminum oxide is an example of, again, because each aluminum atom is surrounded by 6 oxygen atoms, again it is example of octahedral oxygen termination. So this is the actual single crystal of aluminum oxide, but you see, when we see it at the angstrom level or the atomic level, when we see the structure, so you see this is the periodic arrangement that is extending. Another example is magnesium oxide, MgO. This is the actual single crystal of magnesium oxide. It is having again the abscissa structure, and its structure is kind of sodium chloride structure. We have seen in sodium chloride structure, sodium and chloride ions are arranged alternatively. In magnesium oxide also, magnesium and oxygen atoms or ions are arranged periodically. So this is the structure of magnesium oxide single crystal. Now we are going to discuss what we have described about single crystal or crystalline state in a more detailed manner. So the crystalline state, a solid is said to be a crystal if the atoms are arranged in such a way that their positions are exactly periodic. So if we look at this picture, we have a definite periodic arrangement. When we move from point A to point B along X direction, and we have made a translation by amount A, so we encounter another atom. Then again we move by a distance A, again we encounter an atom. So whenever along X direction we move by an amount A, we find an atom. So this is periodic arrangement along x direction. Similarly, if we move along y direction by an amount b, we will find the same type, we will find an atom, or we will encounter an atom. So this is periodic arrangement of atoms, and this is just any arbitrary example. So this is what is seen in case of crystals, that crystals have periodic arrangement of atoms. So along this direction, we are moving. If we want to go from one atom to another atom, we need to move distance a. And if we want to move along y direction, then we need to move a distance b. Then we will find another atom. These a and b along x, or the x and y axis may not be orthogonal to each other. By orthogonal, we mean the x and y axis may not necessarily be perpendicular to each other. They may have some angle lesser than 90 degree. A perfect crystal maintains this periodic arrangements or repeativity of atoms in both x and y directions, from minus infinity to plus infinity. And so far we are discussing the two-dimensional case. That's why we are considering x and y directions. When we consider, or when we think of a crystalline solid, it is a three-dimensional solid. So this periodic arrangement will extend from minus infinity to plus infinity in x, y, and z directions respectively. So look at this picture. It follows from the periodicity that the atoms A, B, C are equivalent. Atom A is here, atom B is here, atom C is here. So, and we are saying these atoms are equivalent. Why these atoms are equivalent? If I am here, and you imagine an infinite arrangement of these atoms. So if I look if I am at atom A and I look around, I found the same arrangement and orientation of atom. If I am at atom B, I find the same type of arrangement and orientation of atom. If I am at location C, I find the same type of arrangement. But don't get confused from this picture, because here it is terminating here. But you should imagine that atom is also in this direction, and atoms are also in this direction also. So this is extending. Otherwise, you can say that atom A is having 3 atoms on the right side, atom B is having different arrangement, but atom C is also having different arrangement. But if you visualize it from minus infinity to plus infinity in x and y direction, then these points A, B, and C are equivalent. So in other words, to an observer located at any of these atomic sites, the crystals appears exactly the same. When we say the crystal is exactly the same, it means that arrangement and orientation of atoms, or a group of atoms, is same when the crystal is viewed from position A, or when it is viewed from any different position. So this is example of a crystalline solid. Atoms are arranged periodically. This idea of periodicity is often expressed by saying that crystal possesses a translational symmetry. So symmetry, I believe you understand what is the meaning of symmetry. For example, if we consider ourselves, and we divide ourselves in a half, so our right portion is symmetric with respect to our left portion. So our body is also symmetric. And by translational symmetry, what do we mean by translational symmetry? As the crystal possess this type of symmetry, that if the crystal is translated by any vector, joining two atoms, and this crystal is translated by a vector denoted as T. The crystal appears exactly the same as it did before the translation. In other words, the crystal remains invariant under any such translation. Invariant means something is not changing. So when we are performing translational operation inside the solid, this means that crystal remains invariant under a translational operation. So as I told you, here this translation operator is represented by R, and here I am saying T. So both are the same thing. In some books it is represented by R. In other books it is represented by T. So for example, first I am here and I translate along this direction, and now I move at this point. So I find the same type of orientation and arrangement. Then I say the crystal is translationally invariant. So we are talking about a perfect crystal. Perfect crystal means the periodicity of atoms or group of atoms extends from -infinity to +infinity in plus x direction. It does the same thing in y direction. It does the same thing in g direction. So that is the meaning of perfect crystal. But actually in a real world, nothing is perfect, and the same thing applies for the crystals also. And the reason being that because the crystal we are considering is having finite shape. It is not infinite length or area or volume crystal. It is having finite size. So by finite size means that it is having some surface, and at the surface this periodic arrangement will break. The periodicity will be broken at the surface of that crystal. So the atoms near the surface see an environment different from the environment seen by the atoms inside the volume of the crystal. So because at the atoms the periodic arrangement breaks, therefore what we will have at the surface is unsaturated bonds, or these are also known as dangling bonds. But inside the volume of the solid, all bonds related to an atom or group of atoms, they are saturated, means they make bonds with other atoms or group of atoms. So another problem why perfect crystals do not exist is because we are dealing the solids at finite temperature, and due to this finite temperature, these atoms are vibrating vibrating around their equilibrium positions when the temperature is greater than 0 Kelvin. And because of these vibrations, the crystal is always distorted to a lesser or greater degree depending upon the temperature. Lesser is the temperature, lesser would be the lattice or atomic vibrations. So lesser would be the imperfections in the solid. Larger is the temperature, greater would be the vibrations of lattice or atoms, greater would be the imperfections in the crystal. The third type is that no matter how pure we try to make the crystal, always there are impurities. By impurities we mean, for example, we are making a silicon single crystal, and no matter how pure we make it, there will be impurities of other elements in this. Even that impurity may be parts per million or parts per billion, but still some impurity exists. Even with the best crystal growing techniques, there are certain techniques by which we grow single crystals. One is the technique is known as the Jokralski technique for the single crystal growth. The other technique is float zone technique. Other technique is metal oxide chemical vapor deposition technique. There are several deposition techniques available nowadays, but still some impurities remain there that spoils the perfect crystal structure. So what are the factors that that break the perfect crystal structure? One is because the crystal itself is of finite size. It possesses a surface. The other is we are dealing the crystals at finite temperature, and finite temperature leads to atomic vibrations. And the third one is the impurity of other atoms inside the crystal. But what we can do is we can try to minimize these errors. So we can prepare crystals such that the effect of impurity on the phenomena being studied are extremely minor. So if you, for example, if we are considering, if we are measuring the resistivity of a crystal as a function of temperature, for example, we take copper and we want to measure how the resistivity or conductivity varies for copper as a function of temperature. If copper is very pure, then at T is equal to 0 Kelvin, its resistivity should become 0, or conductivity should become infinite. But because there are impurities in it, so we will have the resistivity that is known as residual resistivity at T is equal to 0 Kelvin. But what we can do is we can minimize the amount of impurities. For example, one can isolate a sodium crystal so large means its volume is 1 centimeter cube, means we can have a sodium crystal that is 1 centimeter in X direction, 1 centimeter in Y direction, 1 centimeter in Z direction. So, and we can make this sodium crystal in such a way that the ratio of surface atoms to the atoms inside the volume of sodium crystal is very small. So this is known as surface to volume ratio of atoms. And bigger is the size, larger will be the amount of atoms inside the volume, and lesser will be the amount of atoms in the surface. And if you study about a nanomaterial, in a nanomaterial, the number of atoms at the surface is more in comparison to the atoms inside the volume. That's why the nanomaterials possess different property in comparison to their bulk counterpart. And if we consider very low temperatures mean that temperatures are low enough that lattice vibrations are very weak, because lattice vibrations depend upon temperature. Lesser is the temperature, lesser would be the lattice vibrations. So weak would be these lattice vibrations at lower temperatures that the effect of these imperfections on properties, for example, the optical properties of sodium sample are measured to be negligible. And it is in this spirit that we speak a perfect crystal, that we have reduced the surface to volume ratio of atoms, and we are working at low temperatures. In this sense, we can call a crystal to behave as a perfect crystal. Now we have defined our crystal. Now we want to look inside.
Sir?
Yes.
So Saurabh is asking, why are crystal defects important?
Why crystal defects are important? I told you that crystal defects are important because they affect the properties which we want to measure. For example, we want to measure the resistivity, and we want to measure the resistivity of only particular crystal, for example, copper. But if it is not pure, if it is having some other impurity atoms, then not only we measure the conductivity or resistivity of copper, we also measure the conductivity of that elements also that would be reflected in that. So we are not in true sense measuring the resistivity of copper. So that is one property. Or for example, if we want to study the optical property of any other material, we want to measure the refractive index for particular solid, and if it is having impurity element, then it would change the refractive index of that particular solid which we want to measure. So these are the few examples by which we can understand how imperfections or the impurities affect our physical properties which we want to measure.
Okay, sir.
Okay. So now we have we have an understanding, we have developed an understanding how a crystal looks like, and what is meaning of single crystal, what is meaning of a polycrystal, and what is meaning of when we say amorphous solid. So now we try to look inside what is there inside the crystal. So a crystal we can define in a simple sense. Crystal is made of lattice and basis. So we will understand each term in detail separately. First, we discuss about lattice. A lattice is an infinite set of geometrical points defined by integer sum of a set of linearly independent primitive or basis lattice vectors. The definition looks for now a little bit lengthy, but as we go along, we will understand what is the meaning of this. So a lattice is an infinite set of geometric points or imaginary points defined by integer sums of a set of linearly independent lattice vectors, and these lattice vectors are known as by several names: primitive lattice vectors, fundamental translation vectors, like this. So the lattice looks exactly the same from every point. For example, you look at this. So these points are the geometrical points. These are not atoms. So now we are talking about lattice, not the crystal. So lattice is geometric arrangement of points. So we have these points which have periodic arrangement, and and this is a two-dimensional picture, that these lattice points can be described by a translation vector denoted by T, that is equal to N1 times A1 plus N2 times A2, where A1 and A2 and these A1 and A2 must be non-collinear, because we are talking about a two-dimensional case. So A1 and A2 must be non-collinear, means they should not be along the same direction. So for example, here see A1 is in this direction, A2 is in this direction. So A1 and A2 must be non-collinear, and these are known as the primitive lattice translation vectors or basis vectors. N1 and N2 are any arbitrary integers. So for example, we consider this periodic arrangement of lattice points, or this is a lattice. From this atom to this atom, this is denoted by vector, basis vector A1, and this distance along this direction is denoted by A2. Now by taking these basis vectors or the translation vectors or the fundamental vectors, we can arrange, we can reach at any lattice point in this, inside this lattice. For example, we consider this point P. We consider this point P, how we can reach at this point P from here. So we make a translation equal to A1 along this direction, and then we make twice translation along this direction, that is 2 times of A2. So A1 we moves in this direction, and twice of A2 we move in this direction, then we reach at point P. So this translation, can be denoted by a translation vector that is equal to A1 plus 2A2. And if it is a lattice, periodic lattice, if it is a periodic lattice, then the arrangement of lattice points, now I am calling lattice points because now we have not so far placed any atoms or group of atoms. These are only geometrical points. So when we translate from one lattice point to another lattice point, if the arrangement and orientation of lattice point is same, then it is known as a periodic lattice, or it is by other name Bravais. It is also known as Bravais lattice. If we have the periodic arrangement or the similar type of arrangement and orientation of lattice point, then it is known as a Bravais lattice in 2 dimensions. Similarly, we will see the Bravais lattice in 3 dimensions. Another example of 2 dimension Bravais lattice is, again, we see these lattice points which are arranged periodically, and we define 2 basis vectors by A1 and A2. These are fundamental vectors. So if we want to reach at point P, then we have already discussed it. P can be reached from this point by a translation vector that is given by A1 plus 2A2. If we want to reach another point Q, so we can reach point Q. If we invert it, it will become minus A1, and this is A2. So we can reach at point Q by this translation vector that is equal to minus A1 plus A2. In 3 dimension, when we talk about 3 dimension, and all the solids are generally exist in 3 dimensions. So in 3 dimension, points of a lattice can be reached by a translation vector T given by N1 A1 plus N2 A2 plus N3 A3, and here A1 A2 A3 are the basis vectors or the fundamental vectors, and N1 N2 and N3 are the arbitrary integers. Notice that in 1 dimension, just a minute, I am interrupting you. Sorry for interruption. So in 1 dimension, this definition of a lattice fits with our description of a lattice as being points T is equal to NA, because we are talking about 1 dimension lattice. So any point in 1 dimension, any lattice point in 1 dimension can be reached by this translation vector that is integer multiple of this basis vector A. Very important statement we are going to have is, in 2 and 3 dimension, the choice of these primitive lattice vectors or basis vectors is not unique. It is not unique. We can have any type of, there is no restriction on choosing these basis vectors. There is no unique way we can choose them arbitrarily. And you look at this picture, for example, here we are choosing these vectors as follows, this way. This is define one translation vector, for example, A1, and this along this direction, this is defining another basis vectors. Not only this, we can choose this also. For example, somebody says, I don't want to have this this arrangement, this choosing of the basis vectors. Now I want to choose this way. Okay, well, fine. You can go ahead. You can choose these basis vectors. You can choose basis vectors according to this. You can choose. So there is no restrictions on choosing the basis vectors. And similarly, you can see that we are going to shortly define minimum volume cell. So minimum volume, the choice of choosing the minimum volume or minimum area in 2 dimension is also not unique. We can choose a area like this, or we can choose area like this, or we can choose area like this. But these area which we have chosen, and we repeat them in 2 dimension from minus infinity to plus infinity, then they should lead to the complete lattice structure without leaving any void. हिंदी में बता देता हूं, जब ये यूनिट सेल को हम रिपीट करते हैं, तो रिपीट करने से पूरा लैटिस हमारा बन जाना चाहिए, कोई खाली जगह नहीं रहनी चाहिए. तब हम इस मिनिमम वॉल्यूम को कुछ नाम देंगे, उसको हम अभी शॉर्टली डिस्कस करेंगे. The different pairs of vectors correspond to different choices of primitive vectors. For example, here it is a different set of primitive vectors. This is another set of primitive vectors. This is another